Welcome to Lesson 6E, Reflecting Ground. We keep building up on things and making it more realistic and a little bit more complicated. Last time we talked about absorbing ground. Now we're going to talk about non-absorbing ground, or we'll call it a reflecting ground. And we're going to modify our Gaussian plume equation to account for this. So quick review for the absorbing ground case. We're again talking about the case for buoyancy added. So we have Z equal H equal HS plus delta H at this location of the source at this capital H. And this was our equation, our workhorse equation. I call that equation 5 for that case with the absorbing ground. Now, what about a reflecting ground? We're going to use the method of images, and this is really cool. I was first exposed to that with some magnetic stuff in physics. We're talking about magnetic fields, and then we really use it a lot in fluid mechanics, especially when we talk about irrotational flows or potential flows. So if you look at my fluids book, we use the method of images for a lot of problems there. So let's apply that to a reflecting ground. Again, here's the ground, and our source is at m.js is at capital H, accounting for buoyancy. Now, a reflecting ground means that when the air pollution is coming down in this plume and it's mixing around, instead of getting absorbed into the ground, it reflects off the ground. In other words, it just kind of bounces off and it keeps mixing, but it does not get absorbed into the ground. So it stays in the air. All of this air pollution stays in the air, but mathematically we can model this by adding an image. So what do? We add a mirror image, a reflection of that smokestack, and then put the exact same m.js down here. This is under the ground. You say, well, that's okay. It's under the ground, but this is just a mathematical model, and we don't really think of it as under the ground. What we do then is we ignore everything under here. So everything below the ground is ignored, but everything above the ground, so for z greater than 0, we have to take into account both of these. We simply add these up. We have two sources now, the real source and an image source. And this image source is just added to our equation. And now imagine what happens when we have a reflection. Let me just mention that in this region that's kind of lightly colored here, nothing has changed yet. So the plume is normal out here. We don't see anything different. But in this region, there's an overlap between the top plume and the bottom plume. So here we have two plumes that come together. And we're not creating any more additional mass, actually, because only the part that's reflected goes back in. The rest of this bottom plume is all underground. So we don't consider anything for z less than 0. We just ignore that. So let's pick some point of interest A right here. And so from the top plume, the normal plume, we have this CJ, so we'll call that CJ1 right there. That point on this, we're plotting CJ in the normal case, CJ as a function of Z here. But we have an identical plume underneath the ground, and it happens to be impinging on that point A as well. So that I'll use a different color. That one is this little segment here. So this point is CJ2 from the lower plume. So this one comes from the lower or the image plume or source, and this one is the upper source. So you have to add those two up to get your CJ. I should also draw my U. Everything is a mirror image under here. We have the same U and the same properties. Everything's identical. We just have a mirror image.
It's kind of like identical twins. Yeah, I'm the source and Dick is the image. No, I'm the source and Duck is the image. Good grief.
You know how you see those photographs on a lake and pretend this is water, this ground is water, and you see the pure reflection in still water on a lake. You see the reflection of that plume. Well, that's kind of what we're seeing here. So at A, at this point A of interest, CJA is equal to what we call CJ1 plus CJ2. So you just add them up. This little segment is CJ2 and this big segment is CJ1. You add them up. You're just superposing those together. At a point of interest here, if we take a different point of interest, let's use green here for a point B, right on the ground, you get a CJ from the upper plume and the same CJ from the lower plume. So at B, CJB equal twice the ground absorbing case. And this is true only when you're on the ground. When you're above the ground, that's not the case. So for example, in our point A, we're somewhere above the ground here. The upper upper plume has a bigger contribution than the lower plume. Of course, if you're way up here, you don't really see anything from the lower plume. And so this is true. This double is only true right on the ground. So don't think that it's always a factor of 2. And then I wanted to just mention, as we get into the math here, then how do we actually add this mathematically? Well, this source, remember this top one, the real one, was at z equal h, and this bottom one is at z equal negative h, because it's a mirror image. So in this equation, remember when we did that transformation, we just took z minus the location of the source, which was h. So that's how we got that z minus h to make our z go from the ground up. Well, you do the same thing, except now we'll have a z minus a negative h, or z plus h. So all we do is add that back into the equation. So what we're going to do is add this second source at z equal negative h. And so we can just write it right out, our final equation. Here's all our original stuff. And then we add the second source. Notice the big bracket has this accumulation of constants included in it. So I just added another exponential Gaussian curve with a z plus h instead of a z minus h. And that's our equation. So this will now be another workhorse equation for a reflecting ground. That's really all you have to do to develop this mathematically. So I think this is really cool. I hope you agree that we're able to get this reflecting ground case simply by adding another term with a z plus h instead of a z minus h. That's all there is to it. Let me just give you a summary procedure here for gaseous air pollution from a stack. And this will apply to either ground absorbing or ground reflection. And by the way, you can have somewhere in between where the ground absorbs some of the air pollutant, but not all of it. And then your answer would be somewhere in between those two cases. The ground reflection case is always going to be larger than the ground absorbing case, because we're adding, instead of that air pollution just getting absorbed into the ground, it's kind of bouncing back into the air. So this area that's shaded darker has more air pollution than it would have had with the ground absorbing case, obviously. And we've added a term, and this always adds a positive number there. So the procedure is use the Martin model to determine the class, A, B, A-B, etc. And then you calculate these dispersion coefficients at some x. Then you calculate the effective stack height, hs plus delta h, and then you use one of these equations, either the ground absorbing case or the ground reflecting case. So that's just a summary. And then you repeat for various locations, and that's where Excel or MATLAB or other software comes in really handy. And I hope you're taking my advice, and especially if you've done this part already, you just copy and paste and change this minus to a plus, add that term, and you got your equation there already. And so let's do a quick example, and we're going to do exactly the same example as previously, except the only thing different is now we have a reflecting ground. So we have our stack height, HS, we have our buoyancy, delta H, we have U, 5 meters per second, we have our M dot JS. All of this is the same as before. It's an overcast morning, just like before. And this gives us a class D. So make sure you use the right coefficients for that. The difference here is now the ground reflects, does not absorb the air pollutant on contact with the ground. And let's estimate the maximum mass concentration at ground level. Maximum, meaning that's going to tell us that we're going to do this at y equals 0, maximum horizontally at the ground, which will be directly downwind of the stack. And we're going to use exactly the same x that we used before as well, which is x equal 4.85 kilometers. So plug in all the numbers. Again, if you did this in software, make sure you get the same answer as me and just plug in the numbers. And so we apply this equation at y equals 0 and at z equals 0. So it's y equals 0 because it's the maximum, as I said, horizontally. Z equals 0 means it's right at the ground. So it's right at ground level. And you could do this for different z's. You just put in a different z in your equation. And at x equal 4.85 kilometers. And you should get the following results. The sigmas will be exactly the same as last time because we haven't changed anything with this atmospheric conditions or even the x location. So these are the sigmas that you should get. And then your CJ is 149.3 milligram per meter cubed at this particular your location, this point of interest for those 3 coordinates. And so make sure you're able to get this value. And if you are and do it in Excel or MATLAB or some other software, you should have no difficulty doing the quizzes or homeworks. We'll have lots of different opportunities to put this to practice. Okay, finally, let's do the same thing we did last time and look how ground concentration varies with distance from the stack. So we're going to plot CJ, and I did this in Excel. All I did was repeat this. Instead of x equal 4.85, I used a whole bunch of x's in Excel, filled it all down, and used this equation and generated the blue curve here is reflecting ground, the old one absorbing ground we had last time. And this is at the ground, so notice that it's exactly twice as much. So these are at ground level. So we had set z equals 0. And let's just do a sanity check again. Our point here was at x equal 4.85 kilometers. Last time we had, for the absorbing ground case, 74.7 milligram per meter cubed. And then let's go up that same location to here, 149.3 milligram per meter cubed, which agrees with our answer we had up here. And then finally, I just wanted to mention, since this is on the ground, this is exactly a factor of 2. And again, that is not the case if you're somewhere off the ground. You can see from this diagram that when you're at the ground, it's just a factor of 2, but when you're off the ground, it will be some factor that's not 2.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.